Rest of the free response equilibrium problems that we didn't get a chance to get to in class. So I'll get through as many of them as I can before I get interrupted by somebody walking in my classroom, and then I'm pretty sure I'll have to cut this into two parts, so we'll just see how it goes. So you can read the question here, and it says here that we have 100 grams solid NaHCO3 placed in a previously evacuated 5-liter container. I'm going to kind of underline some of the important stuff. So 100 grams of the sodium bicarbonate, 5-liter container, 160 degrees Celsius. Some of the original solid remain. Now this little statement right here, this is pretty important. This means that this reaction is in a true equilibrium type of situation. If all of this solid was gone, then that means that the equation is still shifted far to the right. So we want to make sure that we do have some solid remaining to make sure that this is a true equilibrium type of situation. Total pressure was 7.76 atmospheres when equilibrium was reached. Calculate the number of moles of H2O. So the first thing that we have to do here is they want number of moles of H2O, and we've got a solid yields a solid plus 2 gases. Well, the 7.76 atmospheres is going to be the pressure of our 2 gases together. So I can very easily calculate the total number of moles of gases that are present in our equilibrium by using everybody's favorite equation, PIV-NERD. And when you use total pressure, then that gives you total moles. So I'm just going to rearrange this for the total number of moles, and that's going to be the total pressure over the times volume over RT. So I'm just going to plug those numbers in. The total pressure was the 7.76 times our volume, which is still 5. That hasn't changed. R, as always, is 0.0821, and our temperature was 160, but because we're using R with the units of liter atmospheres per mole Kelvin, we have to convert that 162 degrees Celsius, which works out to 433 Kelvin. And then you plug all this into your calculator and you get 1.09 moles. Now, this is total moles of gas. We have 2 moles of gas that are going to be formed in this reaction if we're just looking at coefficients here, 1 mole of water, 1 mole of carbon dioxide. So if we want to convert this into just moles of water, well, we can say 1.09 moles total, and in our equation we have 2 moles total, and 1 of those moles is going to be water. And so really we're just taking the 109 and dividing it by 2, and you get 0.545 moles of water. And then B asks, how many grams of the original solid remain? Well, all we got to do, if this is how much water we made, we'll convert it back to the sodium bicarbonate to see how much of this stuff was used, and then just subtract it from what we started with. So I'll switch colors here. So we're going to take this 0.545 moles of water, and we're going to use stoichiometry to convert it to grams of the sodium bicarbonate. So for every mole of water, we're going to use up 2 moles of the sodium bicarbonate. And again, this is just the mole ratio from the equation. And each mole of sodium bicarbonate has a mass of 84.01. Cancel what you can, and mathematically we just end up with 0.545 times 2 times 84.01, and you end up with 91.6 grams of the sodium bicarbonate is what we used. The question asked how many grams of the original solid remain. So to figure that out, we just take the 100 grams that we started with, subtract the 91.6 grams that we used, and that works out to 8.4 grams of NaHCO3 remain. Alright, and then C, write the equilibrium expression for K, that's a P, Kp, and calculate its value. So let me erase what I've got here just to clear up some space. All right, so here we go. The equilibrium expression for K, remember, is always products over reactants, and only gases and aqueous come in here, and with pressure it's only gases. So the only gases we have are in the products. There's nothing in the reactants that would be affected by pressure. So our equilibrium expression looks like this: the pressure of water times the pressure of the CO2, and then because the equilibrium pressure was 7.76, and this is pressure total, which is equal to the pressure of water plus the pressure of CO2. If there were coefficients in front of here, then we would say like 2 times the pressure of water, or whatever the coefficients were would go in front. But this is a 1-to-1 ratio, so that means this 7.76 is equal parts water and carbon dioxide. So that means that the pressure of water and the pressure of CO2 are just simply 7.76 divided by 2, or 3.88 atmospheres. So we take that number, plug it in down here, and so to find Kp, we're just going to simply take 3.88 pressure of the water times the exact same number, because it's also the pressure of the carbon dioxide, and we end up with Kp equals 15.1. And then D asks if 110 grams of solid NaHCO3 had been placed in a 5-liter container instead of the 100, so we added 10 more grams, what would the total pressure have been at equilibrium? Well, remember back when I said some of the original solid remained, which means we were at a true equilibrium? Well, if we had 10 more grams, well, then instead of having the 8.4 grams remaining, we would have 18.4 grams remaining. So it would have absolutely no effect on the total pressure because the reaction had reached equilibrium. If there wasn't any solid left, then adding more solid might or might not have affected the equilibrium pressure. It would have affected it if some of this extra 10 grams that we put in there reacted as well. If none of the 10 grams had reacted, well, then that means 100 grams was enough for equilibrium. But since we had some solid remaining, that means that equilibrium had already been reached, and once you reach equilibrium, you're not going to change anything. Okay, so here is this question, and I'm going to highlight the pertinent information. So here is our reaction right here. SbCl5 yields SbCl3 plus Cl2, and they tell us we have an 80, oh, I need a pen, sorry. We have an 89.7 grams sample of SbCl5, and they're nice enough to give us the molar mass. That's super duper nice. 15-liter container, 182 degrees Celsius. That's all the pertinent information that we need. So they want to know, first of all, what's the concentration in moles per liter? So what's the molarity of the SbCl5 in the container before anything happens? So what is our starting concentration? Well, they gave us grams and they gave us liters. We want our answer to be in moles per liter. Well, we got the liter part taken care of. We just need to convert grams to moles, which is easy enough. So 89.7 grams of SbCl5. And like I said, they were nice enough to give us the molar mass. So 299 grams of SbCl5 are contained in every mole of SbCl5. And then they told us that we had a 15-liter container. Well, since we want moles over liter, our grams of SbCl5 are going to cancel out. So we got moles on top, so let's just plot this liters here on bottom. And now we're in moles per liter. Plug this into your calculator, basically 89.7 divided by these two numbers multiplied together, and you end up with a molarity of 0.0200 molar SbCl5. Number two, what is the pressure in atmospheres of the SbCl5 in a container before any decomposition occurs? Again, if you want to know pressure and you have mass, you have volume, you have temperature, well, that's using, since we have mass instead of moles, we can use the special form of Pivnert that we came up with, Pivomert. PVM equals MRT, where the capital M is the molar mass and the little m is the mass that you are given. So rearrange this for pressure, and we get pressure equals little m RT over V big M, and then plug in all of our numbers. So the little m was 89.7, R is 0.0821. Temperature they gave us as 182, but of course we have to convert that to Kelvin, so it's 455. Divide that by our volume, we had 15, and the molar mass of this compound is 299. Plug that into your calculator and you get 0.747, and because it's pressure, the units are atmospheres. Alright, B. If the SbCl5 is 29.2% decomposed when equilibrium is established, calculate the value for either equilibrium constant Kp or Kc for this decomp. And then indicate what you're calculating for. Now, we have two things that we can use here. We have the molarity and we have the pressure. So we can calculate either one of these things, Kp or Kc. I'll do both. Just to get you guys familiar with it. But of course, if you were doing this, you would only have to pick one. So pick the one that you're just naturally the most comfortable with. So since it says it's 29.2% decomposed, that means it's 70.8% still there. So if we take this pressure, and we know that the equilibrium pressure is 70.8% of this, then that means if this was the initial, then our equilibrium pressure is, take 7.747 and multiply it by 0.708, and you get 0.529. So that's the equilibrium pressure of our SbCl5. And we can do the same thing here. If this is our initial concentration, then our equilibrium concentration is going to be 0.0142 molar. And of course this down here is atmospheres. So what do we do with these numbers? Well, we set up our Rice table. So my equation is SbCl5. Everything's a gas, so I'm not going to put states on here. SbCl3 plus Cl2. My starting concentrations, I'm going to do Kc first, is 0.02, and of course these guys are 0 because no reaction has occurred. I know that my equilibrium is 0.0142, which means to find the change, I just need to subtract these guys. So this guy went down by 0.0058. Whatever this guy goes down by, our products have to go up by. So SbCl3 increased by 0.0058, and so did SbCl2. So my equilibrium concentrations of these guys is just 0 plus that number, or just that number. So to calculate Kc, I'm going to take my product concentrations and divide it by my reactant concentrations. And remember, if any of these guys had coefficients, then their concentrations would be raised to that coefficient. So here I just plug in the numbers, 0.0058 times 0.0058 divided by my reactants, 0.0142, and I end up with Kc is equal to 237. So there's Kc. And then I also said I was going to show you how to calculate Kp. So I'm going to do that. I'll do that up here. Okay, so switch colors. Set up the same thing, but this time instead of concentrations, I'm going to use pressures. So SbCl5, SbCl3, Cl2. My initial pressure was the 0.747, and my initial pressure of products was 0 because no reaction had occurred. My equilibrium concentration of my reactant was 0.529. And so to find out what my change was, exact same thing I did down here, just take that minus that, and you get, this went down by a factor of 0.218, which means these guys go up by the same amount. So their equilibrium pressures are 0.218. So to calculate Kp, we take the pressure of the products and divide it by the pressure of the reactants. And so we get 0.218 times 0.218 divided by 0.529, and that works out to be 0.0898. Let's see what else we got here. In order to produce some SbCl, I'm pretty sure that says 5. A 1 mole sample SbCl3 is first placed in an empty 2-liter container, maintained at a different temperature from 182. So that means our K's no longer apply because our temperature is different. And at this temperature, oh, look at that, they're nice enough to give us K. So how many moles of Cl2 must be added to this container to reduce the number of moles of SbCl3 to 0.7 moles at equilibrium? So let me clean this up here. Okay, so I'm going to go ahead and set up my rice table again. Gotta love these rice tables. SbCl5, SbCl3, Cl2. So my initial concentrations, they told me that a 1 mole sample is placed in a 2-liter container. So since we've got moles and we got liters and we got Kc, obviously I'm working with concentrations. So I've got 1 mole placed in a 2-liter container. So that means my initial molarity of the SbCl3 is going to be 0.5 molar. My starting concentrations of the SbCl5 are 0, and Cl2 is what I'm trying to figure out ultimately. So I'm just going to leave that guy blank. Now they said at the end, they want it to be what must be added to this container, well, how much Cl2 must be added to this container so that the SbCl3 final amount is 0.7 moles. But again, this is moles. We don't put moles in our rice tables. We only put concentrations or pressures. So we need to put a concentration. So if we want our final equilibrium amount to be 0.7 moles contained in a 2-liter container, well, that means our equilibrium concentration is 0.35 molar, which means this has to have gone down by 0.15. Cl2 must also have gone down by 0.15, which means this guy went up by 0.15. So my final concentration of the SbCl5 should be 0.15 molar, and we don't know what chlorine is. So if we solve this, well, then we can add the 0.15 to it and get back to what we originally wanted. So let's do that. So we've got Kc is going to be equal to the concentration SbCl3 times the concentration of Cl2 divided by our reactant SbCl5. So we know Kc is 0.117. We know the concentration of SbCl3, that's the 0.35. We do not know chlorine, so that's going to be our X. And we know the concentration of the SbCl5 is 0.15. So rearrange all this and solve for X, and you get that X equals 0.0501 molar. That's just practically 0.05. So this is what we want our equilibrium concentration to be. And so to get back to the amount that we have to add, well, 0.05 plus 0.15 gives us 0.2 molar. Well, the question didn't ask what concentration. The question asked how many moles of Cl2 must be added. So we just got to convert this molarity back to moles. So if we have 0.2 moles per liter, and we have a container that is 2 liters, well, liters cancel. 0.2 times 2 gives us 0.4 moles Cl2, and then you would put like must be added or something like that. All right, so that is the end of these 2 questions, and we're going to call this one a day, and I will come back and work out a couple more.